Okay, and today we will talk about writing to microcontrollers flash memory. So it's possible that you are working on some project where you need to log some information, to write down some information, and you want that when microcontroller resets or when somebody powers it off and turns it back on again, you want the information to be stored inside the microcontroller or somewhere on the board so that it's remembered during power cycles. Okay, so I'll write it down. We want to store information, and the term for that is in non-volatile memory. So volatile means something that evaporates, it disappears. For example, random access memory, when you switch off the computer, random access memory information disappears. But non-volatile means a memory that retains its information even if the power is switched off. So what types of a non-volatile memory can we do we know? Well, we know, for example, flash memory. It's a technology with which we can store information. So flash memory, we know it's very old. Second one is electrically erasable programmable read-only memory. So also it's a memory that you can buy as a separate chip, or some microcontrollers have it built in. Flash memory is the place where most microcontrollers in modern days have a program. So in microcontroller, it is the memory in which a program is stored. So in flash memory, usually in microcontroller, it's where the program is stored, or it can be a separate chip on the PCB. So for example, you have a microcontroller and then you buy a separate flash memory chip, for example, 1 GB of external flash memory, and using microcontroller, you can write some logs in it. Electrically erasable programmable read-only memory, usually in modern microcontrollers, it's not built in, but some older microcontrollers, for example, 80 mega from Atmel, which is used in Arduinos, it has some kilobyte of Eeprom also built in. So I'll write down some microcontrollers have it built in, or it can be a separate chip. Okay, so the third non-volatile memory, which is something more modern, it's more expensive, but it's so much better, is called ferroelectric RAM. So I would like to talk about it a little bit more because not everybody knows about it. It's not very popular because it's a bit expensive, but it's really good. So let's see. The flash memory, which is built inside microcontrollers, usually it can be erased and rewritten only about 20,000 times. Or I'll write erases. Some other flash memory maybe is more durable, but basically it has some rather limited number of erase cycles. As you know, solid state drives, which are very similar to flash memory, they also can wear out because they have some limited number of erase cycles. The electrically erasable programmable read-only memory, EEPROM, if it's a separate chip, it can have, for example, 1 million erases. But this ferroelectric RAM, this thing can have 1 and then 10 zeros. 10 is something like this. So it's 9, 10, it's 1,000 million billion. So it's 10 billion times of erases. That's a big, big number. It's 10,000 times more than EEPROM. So it has, well, some would say that basically it has unlimited erase cycles. It's just that people have measured this many erase cycles and approximated it or extrapolated it. It's practically hard to destroy it. We will check out a little bit of information on the internet, ferroelectric RAM. So first I'll show you the Eeprom. And the idea in this Eeprom is that it has insulated gate. It's floating gate, basically it's just insulated from everything. And then with high voltage, you can charge it through an insulator and it stays charged and it shows logic 1. Okay, so you can just charge this floating gate by breaking through the insulation, and then it shows logic 1. And then later you can erase it. But since changing its state requires breaking electrons through the insulator, this insulator eventually wears out, maybe only after 20,000 cycles or 1 million cycles in some cases, but actually it just wears out. Similar thing to flash. Flash memory works with similar principle. Again, floating gate, just a little bit different construction, but very similar. And it also wears out. However, this ferroelectric random access memory is built in such a way that it actually has, instead of floating gate, it has some ferromagnetic piece. So when you put current through it, you magnetize it in one direction. And if you put the current to the opposite direction, you magnetize it to the opposite direction. So you can store either magnetization to one side or to the opposite side. And to read this information, you put current through it in one direction. And if the current is big, then you know that the ferroelectric material was magnetized to the same orientation, and the last current that flew through was the same direction. So you, for example, test it for ones, and if it's the same direction, you know that one was stored. But if you try to push the current to that direction, but last time it was magnetized to the opposite direction, the current will initially be smaller because it has to change the magnetization of this ferroelectric material. So the current will be initially smaller. So you know it's smaller, so you know it was magnetized to the opposite direction. So you know that 0 was stored. So this thing doesn't have to break through any insulators or something like that. So it basically is hard to destroy this thing. And it retains the information for many years, maybe even hundreds or thousands of years. So it's very good. And yeah, the number of reads and writes is 10 billion or even trillion times. And but it's a bit more expensive at the moment, so not everybody uses it. But I just want to mention it because the problem with these first two methods is these things wear out. And oftentimes in home appliances, for example, there are many devices that remember the last settings that you put into them. For example, dishwashing machine. Oftentimes they're built in such way that when you turn it on, it automatically shows you the last uh, setup that you use. Then you just press start and it automatically does it. Or if you change it, it remembers the last settings that you used. But every time you do this, the information is written into usually EEPROM. And after some number of cycles, which is usually not really 1 million, usually it's maybe 10,000 or 100,000. But after some years, this dishwashing machine or something like that starts to forget the settings or doesn't work at all because it when it erases the chip, not all bits are erased, so wrong information is stored and some errors can show up. So oftentimes these devices can be fixed just by replacing this EEPROM chip. You disassemble the machine, you find the EEPROM, desolder it, buy a new one on the internet, solder it back, and it just magically starts to work. And also, this problem appears in cars and in some trucks, which also store settings in EEPROM, and you switch on the car and its dash works strangely or something like that. Or the trucks, they modern trucks that are used in agriculture, they have so many electronics inside that using GPS they just travel around the field on their own, and people just, there's a person sitting inside but not really steering even sometimes. And all these settings are also stored there. And it's actually quite common that after some years of work, only maybe 5 or 6 years, this chip goes bad and the truck doesn't work anymore, because in this chip the truck writes down the number of kilometers or even meters that it travels, and the number of liters of gasoline that it's consumed and something like that, all kinds of statistics, and they just wear out. So it's better to use ferroelectric RAM. In such cases, if you know that there will be many writes, just use this chip. It's some like 2 or 3 euros more expensive, but it's almost indestructible. And also, there's a series of microcontrollers from Texas Instruments, which has all of its memory built as ferroelectric RAM. So you can just use the microcontroller's internal flash memory to log data. You don't need external chip to log it. You just write in the same memory location millions of times and it just works. I think it's from MSP 430 FR series. These are the ones that have a ferroelectric random access memory in flash and in RAM, so unlimited times of reprogramming and storing data. But if you have a situation where, for example, these Texas Instruments chips are, for example, don't have the feature that you need, and you have to use a different company's microcontroller, then usually the setup is that you have microcontroller and you have external non-volatile memory. So, and again, it can be flash, flash EEPROM or FROM, and usually they are connected through SPI. And that's a very classic setup for lines, and it just works. However, if we want to be cheap, we sometimes want to use the internal flash memory of the microcontroller. For example, this microcontroller has program memory, which is 1 MB or half of a megabyte of flash. And let's say our program only takes 100 kilobytes. So we are only using something like 10% of the microcontroller's flash memory. So is it possible to use the rest of the memory to store information? And for some microcontrollers, it's not possible, but for some microcontrollers, it is possible. Uh, or I would say it's easy. So if the microcontroller is built in Harvard architecture, then it has separate flash memory and separate data memory. And it's usually hard to write into the flash memory because it's built in such a way that it only stores program, doesn't store data, uh, and writing back to it is problematic. Usually you just write the program one time in the flash memory and that's it. However, if we are using von Neumann architecture, then it's built in such a way that flash and RAM is just memory. It's a single memory, and you can store program, and you can also store and read data. For example, computers are built in such a way uh, because actually to make the computers faster, the code is not executed directly from hard disks, from SSDs, because they're relatively slow, even the newest ones. Usually the program is first loaded into random access memory and it's executed from there. And also data is stored in random access memory. And this is the way that the microcontrollers in ARM architecture are also built. So basically, if we check out our microcontroller, which is ARM architecture, Advanced RISC Machine Architecture, they are in von Neumann architecture, but it's a bit upgraded. And this is the memory of our microcontroller. So the flash memory is in addresses from 0 to 1FFFFFF, and and that's where your code space is. But because all memory is virtually, just aligned as following one another, you can also execute code from random access memory, not just from flash, or you can store data in code memory, in flash memory, instead of random access memory. But of course, there's a special way to do it, but it's possible. And let's check out how we can do that. So I'll write it down. So we can be cheap and use microcontrollers flash memory to store data. For example, we don't want external flash memory because it costs money and we have to solder it and we have to wire it and it's just extra effort. So what if we can use some part of a microcontroller's flash memory to store some data, so that when somebody turns off the device and turns it back on, we can, for example, store some settings in microcontroller's flash, and then when it turns on, it reads the settings and continues to work as if nothing had happened. So it's possible, and we're gonna explore how it's done. So if we are talking about our microcontrollers, and most microcontrollers currently in the market, they have flash memory, and there is a special way to write data to the flash memory. using some functions. Okay, guess this will be the best thing. And we can just skim through the flash memory or the entire memory setup of this microcontroller with some notes. So this microcontroller, just as almost any other similar microcontrollers, has so flash memory. It starts at address 0 and ends at some address which represents the maximum byte of the flash size. So for example, our microcontroller is 1 megabyte. So the address will be such that it shows 1 megabyte of information. But if we check out its expansion, so the code space is subdivided into our flash memory, which is the program. So the program is stored in this flash memory, but the cool thing is that we can tell the compiler to only store our program in some bottom part, and the top part we can use for data. And we can write data, we just need to observe some limitations. But basically we can tell compiler, imagine that our microcontroller, instead of 1024 kilobytes, it has only 100 kilobytes. So it will use bottom 100 kilobytes for program, and the rest it will not touch. And from our software, we can write some data there. There's also a special 1-page long user data sector, which is special because when we write information in user data and when we reprogram our microcontroller, user data is not erased. So the idea is the following. If you have some secret information like passwords or access keys to the server or something like that, you would want to store them in the flash memory. Here, and you can also, using lock bits, which are located here, by burning lock bits low, you can lock the flash memory against reading. So you can write some secret code, you can flash it to the microcontroller, and then you can lock the flash area so that it's impossible to read it. When somebody attempts or forces to read the flash, it just erases itself. So these microcontrollers have this feature, and actually most other microcontrollers also have a feature where you can lock the flash memory against reading. And everybody actually commercially does it. If you try to read, for example, iPhone's flash memory, it will probably also erase itself. It's impossible to read it. It's all locked. So secret information you can also store in the flash memory, because if somebody tries to read it and you have locked it from software using one function, which is lock flash function, they will not be able to read it and it will erase itself. But if you want to store some information that is not a secret, then you can store it in user data page, for example, device ID, so that even if you reprogram the flash, the device will have the same ID and you will know that it's the same device. It's not a different device or something like that. So some information like ID or some settings which are not secret, you can store in this user data page, and it's convenient. And also in the code space, special area of addresses is dedicated for random access memory copying, so that actually you can execute code from random access memory. It's just one-to-one mapping of RAM. So everything that is in RAM is also visible to code space. And you can write some functions in random access memory. and then execute them. Instead of flash, you can run them from RAM. Why would it be necessary? It is usually used during firmware upgrade. So let's say you want to remotely upgrade your flash memory. You can do it. You can send the new program to random access memory and store it. And also you can write some functions which rewrite the flash, but this code that rewrites the flash has to be stored somewhere outside of the flash, because if you do the firmware upgrade and you override the function which performs the firmware upgrade, then your microcontroller will just stop working, or it will start to work in a weird manner because it overrides itself. But if you first uh, put this bootloader or this firmware upgrade code inside the random access memory and you execute it from random access memory, then this code can override the flash and everything works fine, you know. So it's possible in ARM microcontrollers and in ARM processors. It may not be possible in other processors. For example, I think Atmel Arduino processors don't have this feature. This is mostly uh, for ARM processors or similar newer processors. So if you want to do firmware upgrade, you do it in the following way. Um, when you write your code, you can specify that a certain function or a certain library is for firmware upgrade, and the compiler will automatically put it in random access memory area. It will consume some random access memory space, so you will lose some space for variables, but you know, that's something you just take into account, and that's all. So you wouldn't want all of the program to run from random access memory. That wouldn't be as good. But the bootloader or program that rewrites the flash, you would want to tell the compiler to put it in random access memory. And it's actually easy to do. In our Simplicity Studio, where you will do the labs, you just use this directive for compiler, where you, before the function, which is here, for example, called apply firmware, you just define it as RAM function. And what it actually does is it puts an attribute section random access memory as extra information to compiler, and the compiler knows that it should put this function inside random access memory. So it will be put, this function will be put in random access memory. I wonder what's the definition of this. Just empty, yeah. And this function can safely overwrite all flash without erasing itself or something like that. And after firmware upgrade, you can call system reset function, and it resets the microcontroller and it boots into the new program, into the flash. And usually the microcontrollers are built in such a way that all programs start at address 0. So after reset, it just starts from address 0, and that's where the new firmware is written. So it's possible to do that, and we will do a similar thing in lab later. Okay, so the rest of the memory is not that advanced. The code space for these microcontrollers, this is ARM Cortex M3 processor, so its code is 32 bits wide. Physically, it's 32 bits, but from logic perspective, it's 8-bit. So each byte has its own address, but physically they're actually 32-bit constructions. So in the flash memory, you can only write 32 bits at one time. You cannot write, for example, 1 bit or 8 bits. You have to write full 32-bit words. So in and again, in usually, for example, in our labs, we will use on GNU GCC compiler, and it allows us in the project properties set the memory size that we want to use. For example, in the memory layout, we can override the default flash options, and we can say that program starts at 0, which is normal, which is where it usually starts, and we don't change that. So the program starts at 0. But for example, for length, if we want only to use, for example, 128 kilobytes, then in programmer's view, I will write 128 kilobytes. It's 128 times 1024. It's this much, and in hexadecimal is 20000. So in this place, I just write 20000, and with this, I tell my compiler to only use 128 kilobytes of flash memory for program, and the rest of it don't touch, don't do anything. Okay, and I press OK, and it's just saved. It works like this. And inside the code, I can use this microcontroller's memory system controller library, and I can write some information or read some information or erase some information from this top part of the flash memory. So from this part, I can erase it, I can write some data into it, or read data from it and use it as I want. Of course, using the same functions, I can accidentally overwrite my program memory, the bottom part, but well, I just have to be careful and don't do it. Just not make this mistake. And also these lock bits allow us to lock some parts of the flash memory against our own accidental overwrite. So that's pretty cool. And all microcontrollers have it. And in reality, when you work on some real projects for some companies, of course, these companies want to keep their programs a secret against reading, against hackers. So you will always want to use the lock bits. Let's check out device information lock bits flash. Let's see. There is some information about the lock bits and exactly how they work. And with lock bits, you can select which pages you want to lock against different kinds of reading and writing. I hope it has more information about it. Okay, it's not what we need, but generally, I can't find information right now, but lock bits can be protected against reading, against writing, and against erasing. So you can basically make it such that the microcontroller is completely fixed and you can't change anything. Yeah. Okay. Now, let's continue about writing to flash memory. So, so this one I'll put here as a secondary option. So just some things that you need to remember. When you erase flash memory, you erase it to all ones. this is just how it's built. Because it's hard to write ones and easy to write zeros because of some electrical implementation, it's easy to discharge something but hard to charge. So it's built in such a way that when you erase, you do the hard work and you erase the chip to ones, and when you write something to it, you just clear to zeros. So for flash and electrically erasable programmable read-only memory, it's the same. After erase operation, so after erase operation, you tell the chip to erase a page or a block or an entire chip. After erase, memory is set to all ones, or in hexadecimal, it's 0xFFFF and so on. It's all ones. So when writing, you clear some ones to zeros and you get the result. And the next thing, EFM32 flash allows to write before erase. So in each memory location, you can write 2 times and that's it. And after you have written 2 times, if you want to write the third time, you first need to erase. Okay? And this is for the following reason. You can manage the data, for example, how operating systems do this, like Windows and Linux and everybody else, to save flash memory. Windows first writes in a free location, then it marks that it's old data, and new data it writes in another free location, and then in the next one and the next one. And when there's no more free untouched locations, only then the hard disk part is erased to ones, and then it starts over. So to save flash, we need to implement some kind of where leveling. And to do that, instead of erasing data every time we want to write new data, the sectors are marked as old or used, but they are not erased immediately. First, other free sectors are used, and when there's no more free sector, then all of them are erased, because erasing takes time, and we don't want to slow down our computer every time we run a sector full. So it's how it's implemented. So in order to mark which sector is new and which is old and which is unused, these flash memories usually allow 2 writes. So that first time when you write data, you write that it's new data, and then you write the data. And when you want to update the data, you mark it as old, and the real new data you write in a new place. And so you can know which is old data and which is up-to-date data. But I'll show it with an example a little bit later. So the next thing is you can erase only at least one page. So you can only erase by page, not by byte. Let's check it out. In this microcontroller, for example, one page is 4 kilobytes, and that's the minimum erase unit. It's actually written somewhere in this documentation, but I'll just tell it to you. And usually you can find this information in datasheet. So Page size is 4096 bytes. It's a minimum erase unit, and the minimum, well, it's guaranteed that it will work for 20,000 erase cycles. After 20,000 erase cycles, when you erase the flash memory, there's a risk that some zeros will not be upgraded to ones, erased to ones, and you read out fully erased memory. And in some places, instead of ones, it's zeros, and it's stuck at zero, and you cannot uh, write one into it anymore. Um, so it is true for internal and external flash. So you can only erase pages, which is certain amount of bytes. For example, 4096 bytes or 4 kilobytes in our microcontroller that we'll use in lab. That's the minimum erase unit, and you just have to take it into account. So when you organize the memory, if you are using, for example, some file allocation library, sometimes they require that you tell them the page size so that the software can manage it and take into account that one block is 4 kilobytes, and then when it reaches the end of one block, it can erase it and then use it again, and so on. Sometimes you just have to tell it in the settings. Next is for external flash memories, there is something called sectors, which is set of pages. For example, one sector is 64 pages, and then you can erase one sector at a time, or you can erase entire chip with single command. But let's stay at the pages. Okay, so that's all written. And now let's look at an example where, for example, we have some device that needs to count, I don't know, for example, how many meters you have driven with your car. Let's write, example like that. So you have to store information about the number of meters that your car has driven. So it's an odometer, and you just want to write numbers. So number 1 is 1 meter. Then after next meter, you have to write it's 2 meters, then 3 meters, 4, and so on. So after every 1 meter, you have to erase and write again. But again, since we have only 20,000 erase cycles, we cannot just write and erase all the time, because just after 20 kilometers, the flash will be so worn that it will just stop functioning properly. So usually how it's done is we take a memory, this flash memory, it has some memory locations. The flash memory inside our microcontroller is organized in 32 bits, but generally it's, you would use an 8-bit memory, and then you just write each part of the number in its own byte. But in our case, let's say that it's 32 bits for simplicity. Okay, so let's say that we know that cars usually don't drive more than 1 million kilometers. So actually, 32-bit wide memory cell for meter count might actually be enough. So what's the maximum number in 32 bits that we can write? To maximum number is FFFFFF. It's 4 billion, so it's 4 million kilometers. So using a 32-bit memory cell to store the number is actually sufficient. If we knew that if we, for example, build this thing for a spaceship, which will travel between galaxies, then of course this number would need to be much, much bigger. And instead of 32 bits, maybe we would need 64 bits for each number. But on Earth, I don't know, maybe some Mercedes-Benz cars drive 1 million kilometers, or maybe some Toyotas. But most cars drive some like 500,000 or 600,000 kilometers, and then they are so worn that you just trash it, give to metal, and buy a new car. So this is absolutely sufficient to count kilometers. So we will just write it as 32-bit numbers. And to manage this, this thing, so we would just write, instead of writing 1 and then erasing the entire page and then writing 2 and then erasing the entire page and writing 3, because then after 20 kilometers it will be worn out, we will instead write the numbers as, I write 1, then after next meter, in the next memory location, I write 2. In the next, I write 3. In the next, I write 4, 5. And once I have written full page, which is 4 kilobytes, but each memory location is 32 bits, so it's actually 1024 cells or words. Words will be more correct term. So each memory location is 32 bits, so it's 1024 or 4 bytes. So actually we can write in one page, we can write 1024 numbers. So the last one is 1024. And once we reach the end of the page, we erase entire page with page erase command. It will erase all the page, and then we can start from the beginning. On the next meter, I write 1025 and so on, 1026 and so on. And I can store the information with 1 meter precision. And after that, I erase again and so on. Now we need to check out, wait a minute, we have a constraint that we can only erase 20,000 times. So it means that the total number of numbers that we can write is 1024 writes per page, and each page can be erased 20,000 times. So max number is 20,000 times 1024 is equal to, and I'll just multiply these two, is 20 million meters, right? So if I divide it with 1,000, this is just 20,000 kilometers, so it's not enough. So the thing to do here is we would need to use more pages to store this 1 million. So how many pages do we need? For example, 1 million is 1,000 thousands divided by 20. We need 50 pages. And then so we write the first page, then we write the second page, the next, and so on. And once we have written 50 pages, then we erase all of the 50 pages and start over, right? How many kilobytes is 50 pages? So I'll just write down. So 50 pages is 50 times 4 kilobytes is 200 kilobytes. So 50 pages equals to 200 kilobytes. In our case, for example, our microcontroller, we can check out in the datasheet, it has either 1024 kilobytes or 512 kilobytes. It depends which version of the microcontroller you buy. The number of kilobytes is in its part number. So it's sufficient. So we know that we can do this. If, for example, our microcontroller only had 64 kilobytes of total memory, then of course we wouldn't be able to do this and we would have to use an external flash memory. But since we have a microcontroller which has big memory up to 1 megabyte, and we only need 200 kilobytes to store these numbers, then we're actually safe. Okay, but, 1 second. So this is how we evaluate the number of pages that we need. And I will show you the second example, which is more common. So in this case, we just write a number. The question is, let's say we unplug the power. Somebody, wants to fix the car. They remove a power supply and then they attach the power supply again. So how do we find the last entry, right? So as I mentioned, the memory cells that are erased have all ones. So what you would do is after the power is reset, your code just simply looks through all cells from the beginning. And when they find a cell that is all ones, they know this is where the empty memory starts, and you just use the last empty cell, the last non-erased cell that you can find. So this one is all ones. So the real number is one memory cell ago. So it's 1026. And then you continue from 1026, and that's one example. And this is a simple example. But now we will look at the second example. Okay, I'll move around a little bit more. So I'll put it, oops. So that I can show you the second example without this thing being in my face. Transparent selection. Like this. So the second example is this. Instead of just writing a number where you can easily find the last non-one entry, we want to store multiple settings. So I'll draw the memory again. So we want to write all kinds of settings. So we want to log some information. Maybe we want to write down the time of event and then some event code and then some other settings. So, okay, I'll check out an example here. Flash memory. User data. Okay, for example, we have the following information that we need to store. We need to store user data version, and we want to store SIM card PIN. So PIN can be up to 8 symbols, and we want to terminate it with null. And since our memory is structured in 32 bits, we need to make sure that the total length of our data divides by 4. So instead of 9, we need to upgrade it to 12. And this is our user data. So we write down a version. And for example, we have to write down a SIM card PIN number. So if somebody has to change the SIM card, we remove the old SIM card, insert the new one, and we need to store in the microcontroller's flash memory the new SIM card. It's just one small bit of information that we want to store, so it doesn't make sense to store just one number to put an external flash memory with gajillion gigabytes of memory to store one small thing which doesn't change so frequently. So we want to use microcontroller's internal flash memory, small piece of it, to write down a SIM card PIN number. Okay, size of pin is up to 12 bytes. So we just select exactly 12 bytes. Okay. And let's say that the pin number can be, for example, 0xFF, which is equal to 256. So if pin is, for example, 200, the pin number is, for example, let's see, 256 plus 100. 1 second. I'll try to illustrate it with a good number. So let's say that the pin code in hexadecimal is let's say that the pin number is 1023. Pin is 1023. In Flash, it will be 03FF. So basically, in some cases, maybe this is not the greatest example, but in some cases, the data that we store in Flash is equal to FFFF. So in those cases, the algorithm that finds the last entry, you cannot just say, find FFFF, because maybe this data that we stored is FFFF. So in these cases, we have to put some header to our data, which marks that this is the last valid data. And I'll just describe it with an example. So in our case, our protocol will be the following. First, 32 bits is age tag, uh, 0xFFFFFFF means unused memory. 0x, and as I mentioned, you can only erase from ones to zeros. So for example, we can write that when we write new data, in front of that data, the first 32 bits, we erase to FFFF0000, and this thing means newest data. And when we want to write newer data, we have to mark that previous data is old data, so we erase those other f's to zeros. So for example, 0x 000000000 means old data. And after that, we write the actual data. So I'll just show it with an example. Maybe instead of 12 bits is just way too long. Pin number is usually for numbers, for digits, so it fits in 32 bits. And so the protocol in this case will be the following. When the flash memory is empty, it's all just FFFF, right? So I'll just copy it like this. And this is empty memory. And now let's say we want to store pin code, and let's say it's 0x000003FF. So what we do is we have to erase some bits to 0. So in this case, I first mark that this will be the new data. So I write 0xFFFF and clear the top part, bottom part to zeros. And then in the next memory cell, I write the next part, which is 0x000003FF. Also, oftentimes, and for example, Microsoft Windows does it automatically, and other operating systems, after writing data, it can also write some checksum, for example, CRC32. I'll just write optional CRC32 for write error detection. You can, for example, calculate the CRC on the data and append it to the end of your data. So when you, that's the on. So, whoops. So when you read the data after power cycle, you read it. But if, for example, there was some writing error, or you wrote and at that moment the power was switched off, so the write didn't complete successfully and the data is corrupt, you can catch this error, and you can realize that the data is damaged, and maybe you can load some default settings or something like that, or just show it on the display, or do something. And when you are using external memory, well, normally you would always want to append some checksum for your data so you can detect errors. Operating systems are doing it automatically. So in an embedded world, you have to write some code that appends it. And next time that you want to write a different pin code, for example, the pin code is 1234, in hex is 000004D2. So what you do is you write the new data in the next position, 0x. So you first write that it's the new data, FFFF0000. I'll set it to black. Then you write the actual data, which is 0x000000 for the 2. And then this is the reason why flash memory is built in such a way that you can write 2 times. In the top part, you override these top FFs with zeros, 0x00000000. You cannot write some other value. You can only erase ones to zeros. So this is your only option. But then next time when the power is cycled, you just search through the entries and you look for the entry that has a header equal to FFFF0000, and you know that this is the latest data. This is how it's always normally done. So no science here, just common sense. And if you have and once you write to the bottom of the page, you erase all of the page, and then you can store it this way. And if you only have to write small data, small number of times, totally can use internal flash memory, and you don't have to buy external flash or something like that, and do it. Nothing bad about it. I can also mention about write and read times. So internal flash memory of microcontroller can be read almost instantly. It's very fast. Writing takes some time, and you can read about this time in its datasheet, electrical characteristics, flash. So number of erase cycles, 2 cycles. So 2 times you can write between erases, and here's this, there's a maximum number of 2 writes to the same word between each erase due to physical limitation of the flash. No bit can be written to 0 more than once between erases. To write a word twice between erases, any bit written to 0 by the first write should be written to 1 by the second write. Is also something that you have to take into account. So this basically tells you that to save flash, instead of writing 0 2 times, when you write 0 first time, you should write virtual 1 the second time, so that it doesn't try to erase 0 to 0 once more, because it wears the flash. So the correct thing is that you write, I'll write it in red, you actually write 0000 FFFF to save already erased bits. So this is why you have to read datasheet so that you don't make mistakes. Like this, and I'll put it here. So it will work if you write zeros, but it just will be better for the flash memory if instead of 0 erasing one place to 0 2 times, if it's already 0, then you write 1 to it, so it just leaves these bits alone. It doesn't try to erase 0 to 0 again, applying this breakdown erase voltage to them, and make sure that the flash wears out slower. Okay, so that's something that it's nice to know it. And then it also tells you flash data retention at 150 degrees Celsius, 10,000 hours. So it's pretty reliable. If temperature is 85 degrees, it will retain information for 10 years. If it's 70 degrees, then for 20 years. And if it's room temperature, it can be hundreds of years actually. Well, maybe not hundreds, but several decades with no problems. And also it tells you the programming time, 20 microseconds, page arrays, 20 milliseconds or 40 milliseconds. So you have to know it for firmware upgrade. You have to know that when you are erasing and writing, you can calculate the total time that you need to reprogram the entire chip. And you have to make sure that nobody switches the power off during that time. Um, to make sure that nobody powers down the device during uh, erase and rewrite process, you should put big capacitors next to device and measure their voltage. If the voltage of the capacitors indicates that it's full, it's 3.3 volts, and they're fully charged, and you measure that when you unplug the device will still operate for some like 100 milliseconds, then you know that you can do the erase. And even if somebody unplugs the device, until the capacitors discharge, it will have enough time to reprogram itself. And if the voltage is lower, it indicates that somebody has already switched off the power and they're discharging slowly, and you should not perform this firmware upgrade, for example. And you have all kinds of currents here. So when you design your device, just take this into account. Okay, so I guess I have told you all of this theory about writing to internal flash memory. So I guess that's it for today.